Here we have again this situation with the sane and demented. 20% of the sane going to the demented, 10% of the demented going to the sane. If we go back to numbers, 500 sane and 500 demented this time, we see that the 20% of the sane will be 100 going this way, the 10% of the demented will be 50 going this way, giving us a net flow of 50 from sane to demented. So we're taking 50 away from the sane and putting it into the demented category. We then get 450 sane, 500 demented, and we can repeat the process. Okay, we have a flow of 90 sane toward the demented, 20% of 450 is 90, and 10% of 550 is 55. That's our flow from the demented toward the sane. So we have a net flow of 35 from sane to demented, and that'll leave us 415 sane, 585 demented. And of course the process can be continued. Now we review what we did when we multiplied the matrices. We multiplied a row vector by a column vector. First of all, if we multiply 0.20, 0.90 times the number of sane and number of demented, we get the number of sane and demented after one transition. 0.20, 0.90 times 500, 500 gives us our 20% of 500. That's the 20% of the sane that become demented. And the 0.90 of the 500 demented, which is the 90% of the demented that stay that way. So we see that we have the 100 sane, 100 demented that become sane, and the 450 demented that remain that way, giving us our total of 550 demented. Again, looking at the numbers, see we have the 10% of the 500 here, the 20% of the 500 here, leaving us in the same category, 80% of the 500 plus the 10% of the 500 that came over here, the 50. Here we see the 90% of the 500 that remain demented gives us the 450, and the 100 is the 20% of the sane that came over here. We then proceed to set up our transition matrix as before, and this is the same thing that we saw earlier. 80% of the sane plus 10% of the demented gives us the new number of sane. 20% of the sane plus 90% of the demented gives us the new number of demented. So that if we look at the numbers, if we had, let's say, 600 sane and 400 demented, 80% of 600 would be 480, 10% of 400 would be 40. The 480 would represent the number of sane that remain sane. The 40 would represent the 10% of the demented that become sane, and similar interpretations are made down here. The 120 is the number of sane that become demented. The 360 is the number of demented that remain that way, the 90% of the 400 that remain demented, giving us our result. Now it might seem like we're flipping around the numbers a little bit, but we're using the same transition matrix as before. We're using, let me just check my numbers here, I'm not sure that we ended up, yeah we did, okay. On the last clip we did, or the last part of this clip, on the last page, we ended up with 520 and 480. So what we're doing is we're taking the transition matrix and multiplying it by our new population, the 520, 480. Of course, the 520, 480 came from multiplying the transition matrix by the 600, 400. Okay? So that if we replace the 520, 480 by this matrix product, we've replaced an equal by an equal, so that doesn't change anything. So we say that the following year's populations will be the result of multiplying the transition matrix by the product of the transition matrix with the original population. So to get the population at the end of 2 years, we start with the original population, multiply it by the transition matrix, and then multiply that by the transition matrix again. And in fact, if we want to figure 10 years or 20, we could multiply this population by the transition matrix and then multiply that by the transition matrix, and we could repeat the process as many times as necessary. we would probably just go to derive and author the transition matrix and take the power of it. That would be a whole lot more efficient. Okay, then we have the, this product, implicitly here, we're thinking of multiplying this transition matrix by this, and then multiplying the result, which is the 52480, by this. We could equally well have changed our grouping and multiplied the two transition matrices together. Okay, if we multiply the two transition matrices together and then multiply by the original population, the 600, 400, turns out that we get the same result because matrix multiplication is associative. It obeys the associative law. Now let's be real clear about something. It does not obey a commutative law. It doesn't obey all the laws that numbers do, but it does in fact obey an associative law. We're not going to prove that here. That's more appropriate to a linear algebra class. Linear algebra kind of picks up where we leave off with matrices here and goes into things that you wouldn't believe. It's amazing stuff. I recommend it. However, you see again that this product up here, which would give us our 2-year population, because we're multiplying the transition matrix by our 1-year population, is the same as multiplying the transition matrix by this product. By the associative law, we can group the two transition matrices and multiply those by the 600, 400, the original population, and get the 2-year population. So we're going to look at how that works in a minute. So you might want to think about how you go about multiplying this matrix by this matrix. Remember that when you multiply matrices, you have to multiply rows of the first one by columns of the second. That, incidentally, is why matrix multiplication is not commutative. If you have two different matrices, then the rows of one and the columns of another are going to be completely different, and when you switch the order, it's not going to work. Anyhow, think about how you would go about multiplying these two matrices here.